Here we're going to talk about how to calculate integrals and areas under curves using integration. In my previous video, I introduced what an integral was and gave you a conceptual understanding of that, so please watch that video before you watch this one. So we're given a function f prime of x, so it's the derivative of some function f of x, and the equation of that is 1/10 x squared minus 2. We were asked to find the function f double prime of x and the original function f of x. So f double prime of x, we know that's just the derivative of the derivative. So we're already given the derivative, so we can just find the derivative of the function that's given. So if I just go down here, so our original function is quadratic, so if you remember, what's going to happen to this derivative here? Well, if we sort of look at some tangents here, at the beginning of the curve here, we have a tangent. That's not a very tangent line. A tangent that's clearly negative. And here we have a tangent that's going to be 0. And then here we have a tangent that's positive. So we should expect the derivative of that to start off as a negative value, right, over here, or maybe down here. It's going to reach 0 at an x value of 0, and then it's going to be positive over here. So we would expect it to be maybe something like, if we have negative over here, something possibly like that, right? A negative slope to 0 slope to positive slope. We can also find this by taking the derivative of f prime of x. So f double prime of x, if we just look at our derivative there, it's just going to be, bring that 2 down, so 2 over 10, which is 1/5 x, and that's it, 1/5 x. And if you look at our graph, it's sort of roughly the right shape, right? So instead of a dotted line, I'm just going to make that a solid line, roughly like that, with a rise of 1 and a run of 6, approximately. It's not exact, but it's the right rough idea. The next question is part A. I did it in a little bit of a funny order, but there's a reason for that. So the question here is, if f prime of x is the derivative of a function f of x, what does f of x look like? And if you think about it like this, remember this function here, in that case, is going to represent the derivative of this function up here. So there's a few things we can look at. What are some key values of that function? Well, here and here, what do we know about our original function? If this is the derivative, that means the slope at these 2 points, the slope of our original function is going to be 0, right? Because, again, this graph represents the derivative. So if the slope of the graph is 0, that means those are going to be horizontal tangents at sort of a little bit past 4 on each side, positive and negative. So, I don't know, I'm just going to sort of sketch this up here. I don't know what it's going to look like, but we're going to have a point there with a horizontal tangent and like a point there with a horizontal tangent. Again, this is just, I don't know, I might need to erase those in a second, but just to get sort of an idea. The other thing is, where is this derivative graph positive and negative? Well, it's positive here, it's negative here, and it's positive here. What does that mean in terms of our function? Well, it means our function has a positive slope here, has a negative slope here, and a positive slope here. So it's going to have a positive slope here, right, in this region. It's going to have a negative slope in this region and a positive slope in this region. So if you think about it, one possible answer for this is a positive slope going up to that maximum. So this all has a positive slope. And then it has a negative slope going to this minimum. Now, obviously, I drew it up there, so obviously this isn't right. It should have a minimum value with a horizontal tangent like that. And then it's going to be a positive slope again. So we would expect it to be a cubic that looks something like that. And that is roughly it. Now, as we've talked about previously, is this the only possible graph for this? And the answer is no, because does it have to be there? Couldn't we draw a same graph with the same properties of the slope, something like this? Right? It still has that same 0, well, approximately, I didn't draw very good, and it still has that same horizontal slope there and there. So both of these are technically answers to that. So let's just zoom out a little bit. At the bottom we have a little note, and the idea is when we go from here to here, the process here is called differentiation, and the process to go from the function to its derivative is called differentiation as well. This process of moving backwards by finding the function that has a slope, that's where the integration comes in. That's called taking the antiderivative or integration. Okay, and it's the same thing. If we were to go from this function to this function, that is also integration, right? If we look at the line as the derivative of a function, we know the function is going to be a quadratic. So essentially, that's in summary. Now, notice we didn't come up with an equation for our original function, and that's sort of going to be the topic for this lesson. So we're going to leave that out for now. We'll move on, and if you want to come back and answer that yourself later, you can. So now let's try to take some of the integrals of some of these functions. So it's asking us here to find the antiderivative of the following functions. So that means we want to find a function that has this as its derivative. So we have here a linear function, and we know that probably the thing that's going to give us a derivative as a linear function is going to be a quadratic function. So what that's going to look like is, well, think about it, it's going to be quadratic, so we know it's going to be something x squared. And if we take the derivative of x squared, what are we going to get? Think about it, you're going to bring down the 2, and that's what you get, right? So the way we write this is we would say this, and that long S shape, that stands for the integral. It's a long S, and it stands for sum, but it just essentially means the integral. So that's the integral of f of x is just equal to x squared. Now it's not just x squared, because remember, look at our previous example. It could be x squared, or it could be shifted up or down, right? It could be like this graph where it could be this one down here, or it could be this one down here. So we don't actually know what the function looks like, so we have to say plus c, plus some constant value, which is going to move it up or down. So that is our integral of f of x, or our antiderivative of f of x. So that's a pretty simple example where the derivative worked out, or the integral worked out nicely. Let's try a little bit more of a complicated one. So we want to find the antiderivative, or the integral of f of x. So we want to find the integral of f of x. Oh, I actually forgot something in the previous one. It's not just the integral of f of x, it's the integral of f of x in terms of dx, in terms of x, the variable x. So we do need to include this part here, which I forgot completely about. So this actually should be, let me erase. Good enough. It should actually be the integral of f of x dx. Okay? It's sort of like when we take the derivative, we do dy by dx to show that we're taking the derivative in terms of x. We have to include that same dx here for the integral to tell us that we're taking the integral in terms of x. Okay, so the integral, let's think about it one piece at a time. So what's going to be the integral of 6x? Well, we know it's going to be quadratic, right? So I'm just going to put the x squared part there. And when we take the derivative of x squared, we're going to bring down that 2 to be in front. Well, there's no 2 in front of our function here. We want it to be a 6. So essentially, the number that would need to be there, hopefully you can figure that out, it's going to be a 3, right? Because if we bring that 2 down, it's going to multiply it to give us 6, and then we have our 6x. And then if we go to our second part, 18 is just a constant. And if you think about what kind of derivative is going to give us a constant slope, the thing with a constant slope is a line. And the line with a constant slope of 18 is just going to be 18x. So there it is. That's our derivative, or our integral of f of x. Now, once again, we don't know how far up or down this graph is shifted, so we have to include plus c at the end. All right, so that is our second integral. Third integral. A little bit more tricky now. So the integral of f of x dx is going to equal, again, let's look at this one part at a time. So I know the thing that's going to give me a quadratic is going to be a cubic function, right? If I take the derivative of that, it's going to be a cubic function. So I'm going to need to bring that 3 down. What number needs to be in front in order to give us that 6 that's up here? It's going to have to be a 2, right? And then if we think about the next one, what's going to give us a 4? Well, actually, this is going to be a quadratic, right? So I'm just going to put that x squared in there. What number has to be in front of that to give us a 4 after we bring down that 2? And the answer is a 2. And then what function is going to give us a linear function, or sorry, a constant function? It's going to be a linear function, and just going to be 1x or just x. And then at the end, always we have to do plus c. Because we don't know exactly where these integrals are, we have to do that plus c at the end to talk about if it's shifted up or down. We actually call these types of integrals indefinite integrals. Okay, because it's just the derivative of the whole, or the integral of the whole function, but we don't know how much is shifted up or down. So it's indefinite because we don't know exactly where it is. We only know the shape of it. As we talked about in the previous video, the derivative is the slope of a tangent, and the antiderivative, or integral, is the area below that function, or the area between the function and the curve, or the function and the x-axis. So I've graphed 0.5x plus 1 on this graph. Now, can we find some of these integrals? So let's look down below. Let's talk about this notation a little bit. This here, essentially, we know this means integral, so we're looking for the integral of 0.5x plus 1 dx, just in terms of x. So we're looking for the integral of this function between 0 and 1. That's what that means with the 0 and the 1. So we're looking for the integral between 0 and 1 of 0.5x plus 1. So essentially what this means is if we look at this function, we want to know the area under the graph between 0 and 1. So what that looks like, we have our graph at 0, and we have our graph at 1. The area we're considering here, get out the highlighter, the area is that. The area between the graph and the x-axis, between 0 and 1. So what is that area? And we would say that's the integral of the function between 0 and 1. And if we just think about it here, we can just do this geometrically, right? We have, oops, let me go back to my pen. We have this value, which looks like it's 1.5. Right, so the height of that, and we have a height of 1 here. So we obviously have an area of 1 for that square, and then this triangle, blah, blah, blah. There's actually an easier way to do this. When it's a shape like this is actually a trapezoid. If you remember, the area of a trapezoid is going to be h1 plus h2, so the two heights, the two sides, times, or divided by 2, because it's the average of the two heights, times the width. So in this case, for this first one here, the area is just going to be, I'll do this at the bottom. Actually, no, I'll just do it here. h1 is going to be 1. h2 is 1.5 divided by 2 times the width of just 1. So when we do that, the answer ends up being 1.25. The area of that between 0 and 1 is 1.25. So let me just put that down here. Equals 1.25 units squared, whatever the units are. Okay, so now we're asked to find the integral between, for part B, between -2 and 3. Okay, -2 and 3. Well, that's -2 is right here, right? It's on the axis, and 3. So what shape does this one form? Forms a triangle. So let me just highlight that. That whole area there, blah, 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 blah. It's just the area of a triangle. And we know how to find the area of a triangle. It's just going to be base times height divided by 2. So in this case, oops, put that back, the pen. Area is base times height over 2, and the base is going to be, well, it's 3 over here, 2 over there, so 5. Height looks like it's 2.5 over 2. Which is 5 times 2.5 divided by 2 is 6.25. Okay, so the area below that curve between -2 and 3 is 6.25 units squared. And lastly, the area between 0 and -6, or sorry, -6 and 0. So that looks a little bit trickier because this area here and this area here, right? Because it's between -6 and 0. So it's like two separate triangles. Now, one little trick to add here is that this area down here, because it's below the axis, we're going to consider that a negative area. And the area up here is a positive area. So essentially we have the area of two triangles, and we're going to basically subtract them or add them together, but one of them is positive and one of them is negative. So we do say that this is a negative area and that this is a positive area. So we would say the area of this, it's going to be, again, base times height divided by 2 for both of them. So for the positive one, it's going to be 2 times 1 over 2. And for the negative one, it's going to be minus, so 1, 2, 3, 4 times 2 divided by 2, which is going to give us a total area of 2 over 2 is 1, and then minus 4, which is negative 3. So the area in this case is actually negative, and that just means more of the area is below the axis than is above the axis. Now the next question asks us to determine the antiderivative of f of x and use this value to calculate the integral instead of from the graph. So we just did it graphically. Can we find the areas using the antiderivative? So the function again is f of x equals 0.5 x, what is it? It's plus 1, right? Yeah, plus 1. So we want to find the integral of f of x in terms of x. And we know that the derivative of the linear part, the first part of that, is going to be x squared, something x squared. So this is a little bit tricky. What value, if we bring it down, if we bring that 2 down, is going to give us 0.5? Well, if you think about it, it's probably going to be half of 0.5, right? Because then we multiply it by 2 and it gives us 0.5. So half of 0.5 is 0.25. Squeeze that in there. So 0.25x, and then the integral of 1 is just going to be x, right? Now, usually we have this plus c here because we don't know what the function is. But in this case, we're going to do something a little bit different because we know we want to find the integral just between 0 and 1. So it doesn't really matter what that starting point is. Our starting point is going to be 0 or it's going to be 1. So we don't actually care about that. In this case, what we're actually going to do is we're going to find the definite integral. So that's the indefinite integral, the one that applies to the whole function. The definite integral is going to look like this. So we want to find the integral between 0 and 1. I'm just doing the first example, a from above. The integral of 0 and 1, between 0 and 1, of 0.5x plus 1 dx. And we already know what the integral of that function is. We just need to do it between 0 and 1. So how do we do that? And the answer is we're basically going to take that same integral that we took before, and we're going to evaluate it in 2 spots. So it's going to be 0.25 x squared plus x, and we're going to evaluate it between 0 and 1. So this is how we write that. And essentially what that means is we're going to plug 1 into this integral, and we're going to plug 0 into this integral, and we're going to subtract the 2 of them. Okay, so what that means, what that looks like, I know we're sort of running out of space here, but it's going to look like this. It's going to be 0.25 evaluated at 1 plus 1. So this is the integral at 1 minus the integral at 0. 0.25 times 0 squared plus 0. You'll notice right away this one goes away because that just evaluates to 0. And this one here is going to evaluate to 0.25 plus 1, which is just 1.25. So that's the area between 0 and 1. And that's what this function told us we were going to do. We were going to find the integral between 0 and 1, or the area between 0 and 1. Once again, we had to break it. We had to evaluate the integral in 2 spots, subtract them, and then we got our answer. And if you compare that to how we did it with the area above, notice how it's the exact same answer. You should be able to do this with the other 2 examples and get the exact same answer as well. Just plug in the different values into the 2 integrals. Okay, so now let's do some example problems. The velocity of an object is modeled by the equation shown. Determine the displacement between 0 and 10 seconds. So I'm just going to very quickly sketch the velocity versus time. It's going to be a linear function, and it's going to have a slope, positive slope, and it's going to look something like that, right? Roughly. We want to know what the displacement of that object is in 10 seconds, in the first 10 seconds. So between 0 and 10. And the thing about a velocity time graph, the area below the velocity time graph represents the displacement in that time. So this is actually a physics problem. If you're not sure about why that is or whatever, don't worry about that here. Ask your physics teacher or do some research online. But basically, that's what we're looking for, that area there. Now, that's just the area of a trapezoid. So you could actually figure that out. If you know what this point is and you know what this point is, we can actually figure that out geometrically. But let's do this using integrals, just to see if we know what's going on. So essentially what we're looking for is we're looking for the integral of the VT graph in terms of t this time, right? T is our variable, between 0 and 10, right? So what is this going to equal? Well, let's look what the let's look at what this is here. We know we're going to have a quadratic function, right? That gives us that 3t part of it, right? So we're going to have t squared, something t squared. What number needs to be in front to give us that 3? When we what multiplied by 2 basically is going to give us that 3? And the answer is 3 over 2, right? We basically have to divide 3 over 2. So 3 over 2, or 1.5. 1.5 times 2 will give us 3, right? I'm just going to do as a fraction in this case. So if I take the derivative of that, 3 over 2t squared, it's going to give us 3t. And then for the 6 part, it's going to give us 6t, right? Because it's just going to be a linear function. And again, the way we show it, we're going to need to evaluate this at 0 and 10, and then subtract those two things. So in order to do that, we're going to evaluate it at 10 first. So 3 over 2 times 10 squared plus 6 times 10. That's the first part of this. And then the same thing evaluated at 0. And if you notice, the thing evaluated at 0 is just going to be 0 in this case, right? Because the t parts are going to go away and it's just going to be 0. So essentially our integral is going to be just that function. This comes out to 210. If we look at our units, our velocity was in, it doesn't say our velocity actually. Let's say it's in meters per second. And let's say our time is in seconds. So what unit is this going to be in? Well, think about what we did. We found the area below this graph, and the area below the graph, it's sort of like doing like length times width or whatever. So it's like we're multiplying our units for velocity, which is meters per second, by seconds. And if we multiply meters per second by second, those are going to cancel out, so our units have to be meters. So there we go. There's our answer, 210 meters. Here's another example of work done on a spring. Work is equal to the amount of work done on an object is equal to the area below the force displacement graph of that function. So let's quickly sketch again what we're trying to do. We want to know the derivative. We want to know if the force applied is represented as the equation 250x. So it's just going to be a line like that, direct variation. If this is the force and this is the displacement, so the amount that the spring moves. When springs stretch, obviously it takes more and more force to stretch that spring further, which is why this relationship is like that. And it's usually linear, according to Hooke's law. But anyways, so that's the equation, 250x. So essentially we want to find the work when we're stretching it from 3 to 6 centimeters. So 3 centimeters might be here. X represents our displacement. So that might be 3 centimeters, and this might be 6 centimeters. So the amount of work done in that space is going to be the area below the curve, just between that 3 and 6. So the way we can do that again, you could try to do that geometrically. It's not very difficult. It's just the area of a trapezoid. But if we wanted to do that algebraically using integrals, this is how we do it. We want to find the integral of 250x between 3 and 6, right? And our variable here is dx. Okay? So how do we do that? Well, the integral of 250x is just going to be a quadratic function, right? So it's going to be something x squared. And if we bring that 2 down, what's it going to give us? 250. The answer is 125, right? It's 250 divided by 2. So 125x squared. And we need to evaluate this in two different locations. We need to evaluate this at 3 and at 6. And that's basically what our answer is. That's what we got to do. We just got to plug in 3 and 6 into that equation. So at 6, it's 125 times 6 squared. And then at 3, it's going to be 125 and 3 squared. So the answer here is 3,375. Now again, what are the units? So force is usually measured in newtons, and x in this case is centimeters. So our units essentially are those two multiplied because it's an area. So Newton centimeters. Usually when we're dealing with work, we deal with joules, and joules is in Newton meters. So we would just convert that to meters. But I'm fine. That's not a physics class, so I'm fine with that as your final answer. Notice how essentially what we're doing here when we subtract these two separate things is this is like basically the integral of everything up to 6. So it's like the area of this whole triangle here. And what we're doing with this part is we're subtracting this little area here. And if you take this big triangle and subtract this triangle, you're left with this shaded region here. Essentially, that's what we're doing. So this is another type of question where it has to do with population growth. And what we're given in the question is that the colony is growing at a rate of 150 root T bacteria per day. So we're given the rate of change of the population, essentially. We're given the rate of change, and we want to find the population at a certain point after 7 days. So we're given the derivative, essentially, and we want to find the original function, right? And that's all integration is. So the way I'm going to write this, as d, what do we want to call population? The change in population per time is 150 root T, right? Essentially that's what it means. The population's changing per time according to that, right? So as time increases, the population's actually going to increase faster, right, by that relation of root T. So we want to find what the initial function is, right, so that we can find the population at 7 days. So in order to do that, we need to integrate, right? We need to do the integral of dp dt, and the integral of dp dt is going to just give us, essentially, the original function, the population function. So look at this, how this is going to look. We want to do the integral of dp dt in terms of dt. And if we do this, it's almost like these dt's are going to cancel out, and this integral is going to cancel out with that change, and we're going to end up with just our population. Okay? So to do this, we know how to take the integral of something, right? I'm going to rewrite this actually as 150 times t to the 1/2. Okay? So think about what we're doing when we take the derivative, and we just want to do the opposite of that when we're doing the integral. So notice how it's t to the 1/2. What function, what exponent is going to give us t to the 1/2 after we take the derivative? And when we take the derivative, we subtract 1 from the exponent, right? So to do the integral, we need to add 1 to the exponent. So it's going to be t, and if we add 1 to that, it's going to be t to the 3/2, right? And then we think about what's going to give us the 150. So an easy way to think about that is just divide 150 by 3/2, because we know we're going to multiply it by 3/2 in order to get the 150. So if we just do 150 divided by 3/2, we get 100. Right? So think about when you're taking the derivative of that. 3/2 times 100 is going to be 300 divided by 2, which is 150. So that works out. Now, we're not actually asked to find a specific range here. So this is the indefinite integral plus c, plus some constant c. So essentially what we found is that the population is equal to 100 t to the 3/2 plus c. Now, we are given an initial population of 500, right? So p at time 0 is going to give us 500. Actually, let me put this in function form like that. P at time t. So p at time 0 is going to give us 500, right? So the question is, can I solve for c? Can I figure out what c is now? And the answer is yes. If I just plug in that times 0 here to the 3/2 plus c, that's just going to be 0 to the 3/2. That's going to go away. So c in this case is equal to 500. So we've found that initial condition and used it to find what c is. So our 100% correct equation for pt, we know it has to be 100 t to the 3/2 plus 500. There's our equation. That is our population. So in order to solve for the c, we actually need some condition, some point on the line that enables us to solve for what c is. So now that we know what c is, we can go back to the original question. What asks us the population after 7 days? Well, remember, this is just the equation of the population. So all we need to do is plug in p at 7. What do we get? So if you do this on your calculator, you should get 2,352, approximately, as your population after 7 days. There you go. We just use integration to find the equation for population and basically find the answer. Now, integration gets very complicated. Some of these polynomials are pretty straightforward to find the integral of, but it gets very complicated very fast. So if, in this course, you want to take the integral of something but you don't know how to do it, I suggest to use Wolfram Alpha or another tool like it, and just literally type in integral of and then your function, and it will tell you what the indefinite integral of that function is. All right.